Okay, so as for our next lesson and kind of a weird mix, we have a little bit of review that we're going to go over first. It should be fairly familiar. We're going to tie it into what we're doing, and then we're going to do something completely new. So let's start off with some review. So way back when, you probably in Algebra 1 dealt with square roots. It's one of the last functions you kind of talk about typically, but it should be fairly familiar. So definition-wise, when we talk about roots, what we're really saying is that something is the square root of a number if we have some kind of relationship like this. So if something squared is another number, then a would be the square root. We'd say that a is the square root of b. So let's kind of take a look at that and make it a little bit easier with numbers. So since 3 squared is 9, this is really just saying that 3 is the square root of 9. So nice and basic. So this is something we've already kind of worked with. I'm sure you've done square root of 9, square root of 16, square root of 25, and we've done all those before. So we're just going to go kind of back, review roots, review how to work with them a little bit, and then we'll tie it into what we've been talking about, which is quadratics. So we have a bunch of symbols for this. So if we want to take the square root of something, we use this symbol here. This is the radicand sign, or a radical sign. So oftentimes we have to have the little lip to show that it's there. We need to extend it all the way over anything that we're taking the root of. If you have something in it and then something out, that means we are taking the square root of what's inside, but not what's outside. And then later on, we'll even have a little number here that will tell us kind of how powerful the root is. We don't need to worry about that quite yet. We'll get to that in a couple more units. But for now, we're dealing with square roots. So when we talk about a root, say square root of 9, we normally would write that as 3. Oftentimes for shorthand, if we're just dealing with basic numbers, they'll assume it's the positive root. I mean, technically speaking, when we take the square root of 9, it's 3 or it's negative 3. Or sometimes people will write it with a little plus or minus like that to say that it could be either one. For simplicity's sake, when we're just working with numbers, we'll usually just talk about the positive root, even though the negative one is just implied. So it's always back there. When it comes to solving things, that's when we have to pay a lot more attention to the negative. All right, so this should be familiar to you. You should have seen this before. So let's talk about some properties of roots. Roots function basically as an exponent. So a lot of the same rules that you might be talked about in Algebra 1 for exponents still apply here. So we can split it up. So if we have the root of two things, we can actually separate that. So that's the square root of one times the square root of the other. And that works fine. We can separate them across fractions. So if we have the square root of the fraction, a over b, we can separate that as the square root of a over the square root of b. These are our two most common principles that we're going to work with. So let's kind of look at some examples of how we would simplify roots. Now, when we work with roots, it's very similar to fractions that we need to have them reduced. We can't just have giant roots. It gets really confusing. It makes our math harder to work with. So we're always going to take things and try to reduce them down. So let's look at a couple options for reducing. So we need to figure out what the square root of 80 is. We can dump it into a calculator. It'll give us back a decimal answer typically, but that's not going to be good enough. We don't want to build in rounding or errors. We just want to make it as easy to work with as possible while still retaining all of the information for the problem. So there's two main ways of looking at how to break this down. I'm going to show you both. I really don't care which one you use. First one was what was called the prime factorization or tree method. So in this, what we do is we start looking at 80 and we start breaking it down. Well, 8 and 10 make 80. Each of these numbers we're going to keep breaking down until they are only prime numbers. So 2 is prime, so I can circle it. 4 we can break down to 2 and 2, and those are prime. 10 we can break down into 5 and 2, and those are prime. Once everything's prime, we've done the prime factorization tree of that number. From here, what we can do is, since this is a square root, anytime we have two numbers in it, it can come out. So I have two 2's inside, so a 2 comes out. I have two 2's inside, so another 2 can come out. The only thing left by itself is a 5. So the 5 stays inside the root, didn't have a partner with which to escape. So this is 4 root 5. So the square root of 80, simplified, is 4 times the square root of 5. This is one method. This might be what they showed you in Algebra 1 or maybe even pre-algebra when they talked about roots. I honestly don't know what they showed you, so I'm just going to show you a couple options here. So that's one method. Second method, early on here, would be to look for common roots. So we know things like the square root of 4 is equal to 2. We know that the square root of 9 is equal to 3. So all our basic common squares are things that we're looking for. Square root of 16 would be 4. Square root of 25 would be 5, and so on and so forth. These are numbers that we're looking for. So we can take this and break it up into nice pairs that we can use. So as an example, that same square root of 80, we can actually break up and say that's the square root of, say, 16 times the square root of 5, because 5 times 16 is 80. And then we know square root of 16 is 4. So we'd get that same 4 root 5. It doesn't matter what order you do it in. So let's say you don't see 16. I mean, not a lot of us honestly have our 16s memorized for times tables, but we know 4 goes into 80. So maybe we break it up as square root of 4 times square root of 20. Well, square root of 4 is 2. So now we have square root of 2 times square root of 20. And now 20 we can break up. So 20 is square root 4 times square root 5. Square root 4, that's 2 again. So there's our 2 times square root 5, and we get our 4 root 5. These form the two most basic methods for simplifying roots. You can look for pairs as you do a prime factorization and the pairs come out, or you can break it up into numbers that actually simplify. It'll get you to the same spot. Both methods are perfectly fine. There's also a couple other ways of doing it too. So if you are interested, I can show you like 2 or 3 more ways to examine these in detail. But in the meantime, these will get the job done. It's probably one of these that we were shown before. After you do these, this is a simplified root. That's all we need to do. Let's look at another example, maybe one that's a fraction. So simpler case, we have square root of 4 over 81. So square root of 4 81st. In this case, what we can do is we can actually simplify it separately, top and bottom. So that's the same thing as the square root of 4 over the square root of 81. Each of these are nice and clean. So this would just be 2/9 as we go to simplify it. Maybe another one, square root of 7/16. I think I'm drifting off the camera here. So if we look at square root of 7/16, again, we can simplify that top and bottom. That's square root of 7 over square root of 16. And that would give us square root of 7 over 4. And that's as simple as we can make it. We wouldn't be able to take it any further. Hopefully this is all sounding familiar. Let's just maybe look at 1 or 2 more oddball ones, and then we'll go from there. My poor beat up table here. All right, so how about something weirder? So what if we said something like square root of 10 times the square root of 15? Well, if we looked at each of these, neither of these simplify at all. Square root 10 doesn't simplify. Square root 15 doesn't simplify. But we could actually combine these. Remember, that's the same thing as the square root of 10 times 15 is 150. And this we might be able to simplify. So let's kind of look at 2 different ways of approaching this one. When we multiply things, we can actually keep them together like this. That's square root of 10, square root of 15. Well, 10, that's square root of 2 times square root of 5. 15 is square root of 3 times square root of 5. So we could do this. We have our 2 5s in here, so we can come out and be left with 5 times the root of 6. That's one way of thinking about it. Another way, we can just go straight to 150. Now that's a little bit uglier maybe, but I know that 25 goes into 150 because that's like $1.50. So that's square root of 25 times the square root of 6, and that gives me 5 root 6. We could do this using the trees. And we could have done the trees at any point. So like if I come from this point again, that's square root of 10 times 15, I can do trees on both of these. That's 2 and 5, those are both prime. That's 3 and 5, those are both prime. There's my two 5s. 5 comes out and I have root 6 left over. We could have done the tree on the 150. So I do a tree on 150. I don't know, that's kind of scary looking. But it would effectively just be the same thing. So maybe we look at that and say that's 2 and 75. Okay, I know this is 25 and 3 and 5 and 5. Again, always stopping when we get primes. 2 5s come out. We have a 3 and a 2 left inside. So you can see it doesn't really matter what method you use. As long as you have one that kind of stuck in your head from before, just work with that system and you're good to go. Our goal is just to always take it down to the most simplified form. There should be nothing left inside that can be broken up. So here, 5 root 6 is done because this can only be reduced to a 2 and a 3, and neither of those we can take the root of. Okay, so hopefully that rang some bells and you're kind of remembering it a little bit more. I don't know if they would have shown you this before here in Texas, so let's kind of go and pretend this is new. So when we deal with a root, we have a couple problems. Square roots often don't simplify. They give us an irrational number. It goes on forever. You can't write it as a fraction. And that causes problems when they're in denominators. So if I have something like 2 over root 7, this is not a good format to have it in. We wouldn't be able to put it into electronics and have it work really well because it's going to build in an error. We never want something irrational in the denominator if we can help it. So what we need to do is we need to get rid of that somehow. We have to fix it. So our goal for fixing it is going to be to actually multiply this fraction, top and bottom, by something that'll make it so there's no more root left. So to get that idea, our first case here, where we have square root of 7, is to multiply it by basically the exact same thing. Remember, a square root of a number is basically saying that that something times itself equals that. So the square root of 7 times the square root of 7 is just 7. Square root of 3 times the square root of 3 is just 3. That's kind of what they're supposed to be doing. So that's what we're going to use to try to rationalize these. They should talk about rationalization before for you. It literally just means we're making it a rational number in the bottom. We don't want anything irrational down there. So in this case, I can multiply top and bottom by root 7. If I do that, on top, I get 2 root 7. And on the bottom, the square root of 7 times the square root of 7 is just 7. So this number has been rationalized. It's now good. We have a nice, easy to use denominator. Another example, 2 over root 3. If we needed to rationalize the denominator, we need to get rid of that square root. So I'm going to multiply top and bottom by whatever is in this root to make it cancel out. So in this case, I'd multiply top and bottom by root 3, and I'd get 2 root 3 over 3. If there are other items in the denominator, we don't need to get rid of all. We only need to get rid of the root. So if I had something like 5 over 2 root 6, I don't need to worry about the 2. 2 is fine. It doesn't cause any problems. It's only the root 6 that's causing a problem. So when I go to multiply, I'm going to multiply top and bottom by root 6. That's all I need. That gives me 5 root 6. Down here on the bottom, I get 2 times, and root 6 times root 6 is just 6. So rationalize, this becomes 5 root 6 over 12. So that was the rationalization process. Hopefully that sounds kind of familiar as we go along. Now it's easy enough to get rid of a root that's only by itself or is just a root. It's more difficult if we actually have something adding or subtracting the root. In that case, we have to do a little more work. So let's take our example of 2 plus 1, or 2 over 1 plus square root of 3. This is harder to work with. And what we're actually going to do is we're going to use one of those formulas we talked about last time. We're going to make use of the difference of squares. What we need to do is we need to multiply top and bottom something that will get rid of the root entirely. So we're actually going to multiply by an item called the conjugate. So when we're dealing with a root, or later on tonight, a complex number, a conjugate is exactly the same thing you see there, just with the opposite sign. So the conjugate of 1 plus root 3 is 1 minus root 3. And that's what we're going to use to do this. So if I need to get rid of the root in the denominator here, I'm going to multiply it top and bottom by the conjugate of that denominator. This forms something that now we have to FOIL, just like we did before in our previous lesson. Up top, the 2 distributes, so I get 2 minus 2 root 3. In the bottom, this is a difference of squares. That was one of the terms we talked about last time. So this is going to result in 1 minus, and then root 3 times root 3 is just 3. I'll show off the steps this one time as a reminder. So we do first, that's 1 times 1 is 1. Outers minus root 3. Inners plus root 3. And last, square root of 3 times negative square root of 3 is minus 3. These cancel out, and we just get the 1 minus 3. Sometimes it can be helpful to not reduce or not distribute the 2 across the top at first. This is a case where that would have been true. So if I left it outside, we would have had 2 times 1 minus root 3. Down here on the bottom, we now have negative 2. 2's cancel, and we get negative 1 minus root 3. And that'd be negative 1 plus root 3. So this is now rationalized. There's no odd things happening in the bottom anymore. Let's do 1 or 2 more examples of these just to bring it back in case your teachers didn't talk about it before. So a new example, let's say we have 5 over 2 plus square root of 5. We want to get rid of it. So our step is to multiply by the conjugate. The conjugate's always the same thing that's there, just the opposite sign. So I multiply it top and bottom by 2 minus root 5. Doing so, on top, I just have 5 times 2 minus root 5. I'm not going to bother simplifying yet. On the bottom, again, we're going to get a difference of squares, just like we did up here. The middle terms will cancel out. So 2 times 2 is 4. Square root of 5 times square root of 5, and it's a minus, would be a minus 5. So that gives us 5 times 2 minus square root of 5 over, in this case, just negative 1. Divided by negative makes the whole thing negative. So we get negative 5 times 2 minus square root 5, and then we would just simply distribute. So this is negative 10 plus 5 root 5. Now, when you rationalize, you're not going to necessarily cancel out the entire denominator. That's just happened here because of what we did, but it's not always going to work like that. Let's do one last one here, and then we'll move on to our next topic. So one more rationalization, simply because we're going to have to do this in our next part as well. So nice, and how about another one? 3 over 7 plus square root 2. All right, so we can't have a square root in the denominator, so we go to rationalize it. I multiply it top and bottom by the conjugate, and now I distribute. So on top, that leaves me with 3 times 7 minus square root 2. On bottom, that's going to give me a 49 minus 2. Again, if we went back up here and FOILed that, the middle terms would cancel, and we're left with effectively this just being a difference of squares. So that gives us 3 times 7 minus root 2 over 47. And then we simply distribute the top because nothing else is going to cancel. So we get 21 minus 3 root 2 over 47. That is our rationalized answer. Okay, so let's take properties of roots to the side. This is a nice quick review. Let's talk about what we're going to be doing with them. So in the previous lesson, we were solving quadratics. We solved them via factoring. The problem is that a lot of things are not factorable. We need other tools. So the second item in your toolkit from Algebra 1 was typically to use square roots. So let's kind of look at an example of that. So let's say we have 3x squared plus 5 equals 41, and we need to solve this. The first hint that we can use roots to solve it is there is no x term. We only have x squareds. If there's an x term, it gets a lot trickier. We have to be able to factor it first, and it becomes kind of messy. It's going to be a big hint that we can use roots to solve things if we only have an x squared term. So to solve this, what we need to do is we need to isolate the root. We need to get this, isolate the squared power. We need to get the x squared completely by itself. So what I'm going to do is I'm going to subtract 5 from each side. Gives me 3x squared equals 36. And I need to divide by 3. We have to have the x squared isolated. So I get x squared equals 12. Now, a square root and a square power are complete inverses. They cancel each other out. This is how we use our square roots. So I'm going to take the square root of both sides. Square root and x squared cancel, and we get x equals. Now, before at the beginning, and when you talked about roots before, you always said that they were positive as you worked. But when we solve, that is not the case. It could be positive or negative. So to mark that, I'm going to write it as plus or minus root 12. Root 12, we need to reduce. We're not done with it. So I know that root 12 is the same thing as square root of 4 times square root of 3, and square root of 4 is 2. So my answer is x equals plus or minus 2 root 3. Now, I will say that sometimes taking roots can mess things up. It's not all that often that it'll mess things up when we're working with quadratics. Later on, it can tend to give invalid answers, just like what we saw before. But for the most part, as long as we're dealing with an x squared, it's going to work out fairly well. So we get 2 possible answers. We get our x is positive 2 root 3. We get an x is negative 2 root 3. So let's look at another one. All right, how about 1/5 x plus 3 squared equals 7. That's kind of a weird way to look at it, right? But we still need to solve for x. I can still use a square root to actually solve this. So I can multiply both sides by 5 to get rid of whatever is in front of it. Because again, our goal is to solve for whatever is being squared. So this would give me x plus 3 squared equals 35. Now I can actually take the square root of both sides. So I square root and I square root. The square root and the square cancel. And I have x plus 3. Over here, I have plus or minus the square root of 35. Square root 35 does not simplify. Can't do anything with it. So as my final step, I'm going to subtract 3 from both sides. Please note that that square root is very similar to parentheses. Things can't just go in and out of it easily. We have to follow that process that we talked about earlier. So the 3 does not go in there. I basically get x equals plus or minus root 35 minus 3. If we wanted to show both answers clearly, that's root 35 minus 3 or negative root 35 minus 3. But I'm okay with you guys leaving it as plus or minus root 35 minus 3. That would be our solution. Those are our 2 ones. Okay, let's do another solving example real quick. We'll talk about application of this, and then we'll move into our next topic. So how about 7r squared minus 10 equals 25. So here's our next example. Again, our job is to solve it. In order to solve, we check, okay, is there r squared? Yes, we have something being squared. Is there any other r's? Nope. Okay, so we're good to use square roots. So my first step is always to isolate it. So I add 10 to both sides. Gives me 7r squared equals 35. I need to have r by itself or whatever is being squared by itself before I can do anything. So I get rid of the 7. Leaves me with r squared equals 5. And now that the thing being squared is by itself, I can take the square root of both sides. Square root and square cancel, and I get r equals plus or minus root 5. Can't do anything with that. It doesn't simplify. That's my answer. All right, so for each of these sections, people are always going to ask me, well, what can we use these for? Quadratics are honestly one of the things that are actually easily applicable to a lot of stuff. Nice one if you've taken physics. As an example, let's see, in US measurements anyway, an object under free fall basically falls as a parabola for short distances. When we start talking about air resistance, that kind of messes it up. But if we just drop an object, the height of that object is equal to negative 16 t squared, where the time is how long the object has been falling, plus h naught, where h naught is actually how high the object was when it started. So let's say I decide to throw a basketball off a 100-foot tall building, and I just drop the basketball. Here's my fantastic art skills. That's a huge basketball. So if this thing right here is 100 feet tall, we can actually calculate how long it will take for it to hit the ground. So I want to know when it hits the ground. That means it's coming all the way down and it's hitting down here at a height of 0. So I have 0 equals negative 16t squared plus the height that it starts at. And we're starting at 100 feet up. This is now a quadratic equation. I can calculate exactly how long it will be until the object hits the ground. So in this case, I go to solve. And since we're talking a real world example here, we're not going to worry about keeping the roots nice and clean. We can actually dump it right into a calculator and find out what we get. So here, I'm going to follow the same process. I need to solve. So I'm going to move the 100 over. I get negative 100 is equal to negative 16t squared. I can divide both sides by negative 16. And again, I'm looking to make sure that I get the squared thing isolated first. So that gives me t squared equals whatever 100 divided by 16 is. Let's get a couple decimal points just to keep it going. I'm not going to make you follow sig fig rules right now. Just keep it fairly reasonable. All right, so we get 6.25. And now we can take the square root of both sides. If we do that, we get t equals plus or minus. We dump square root 6.25 into our calculator. And this one actually works out nice and neat. So we get plus or minus 2.5. Now, one of these answers does not make any sense. This is the time since you dropped it. It doesn't make any sense for the ball to hit the ground before you let go of the ball. So our negative answer makes no sense. Our time would be 2.5 seconds. So it'd only take that ball about 2.5 seconds to hit the ground if we dropped it off a 100-foot tall building. So this is our first example of this. This actually works in metric system as well. The only thing that changes is this number right here becomes negative 4.9 meters per second squared instead of negative 16 feet per second squared. All right, so that's it. That's kind of what we're done talking about for our first topic. So most of our problems are going to be simplifying roots and then solving actual equations that are already in this format. So let's start looking at our second topic for today. So what if we had something like x squared plus 25 is equal to 0? Well, we probably looked at this before. If we talked graphing wise, and we graphed this following our rules, we'd get something like this, where this is about 25 feet up. Okay. Well, it's not touching the axis, so we'd get no answer. Well, how about if we try using our new root method that we talked about that you did before too? So I could subtract 25 from both sides, and we get x squared equals negative 25. Take the square root of both sides, and we get x equals plus or minus the square root of negative 25. And this presented a problem. Dump it into the calculator, you get an error, doesn't like it. Teachers before said, oh, can't take a square root of a negative, so we're done. The problem is that we actually can. So a long time ago, a guy kind of was looking at numbers and things weren't working. He wanted to work with something called the fundamental theorem of algebra, which basically says that whatever the power is of what you're working with, that's how many answers there have to be. And he came up with this whole other idea of ways of numbers that can work. If you're curious, I can link some really fun videos that talk about it. I might show a couple of them as well. But for right now, what we're doing is we need some way to deal with roots of negatives. So our whole problem is just that negative sign. Well, we know we can break up roots. So we know that the root of negative 25 is the same thing as the root of 25 times the square root of negative 1. Well, root 25 is easy, so that's 5 square root of negative 1. And this is where we got stymied for a long time. So what if we could work with that square root of negative 1? What if there is actually something that works? And there actually is. So what we're going to do is we're going to define a new number to be the square root of negative 1. I'm not going into a whole lot of detail what it is. Basically, it involves three-dimensional mapping of things. When we look at it, there's a whole other dimension of math beyond just real numbers. We have also complex numbers. So this is our basic complex number. We're going to define the square root of negative 1 is I. Make it a little cursive lowercase I. This forms our basic complex number. Generally, a lot of times people will call them imaginary. It's not really the best name for them. That's actually a huge con job done by one of the guy's enemies that didn't like him. And since the guy who created this was kind of an unknown at the time, a more famous person that didn't like him actually put out all this bad press. He called them imaginary. Other people kind of joined in because this guy was more famous. And he did such a good job that we still call them imaginary to this day. The creator, who for some reason I can't think of the guy's name off the top of my head, wanted to call them lateral numbers. And eventually we ended up calling them complex numbers because they're more complicated than our basic real number system. So as I warned you guys at the beginning of the year, we are going to step outside of just the real numbers. So let's kind of take a segue here to our number system. When we talk about numbers, we have the natural numbers, which is honestly what comes naturally. That's also sometimes called the counting numbers. Those are 1 or 2 or 3 and so on. We have our whole numbers. That's where we added 0 to the mix, thanks to the mines, as well as Gupta, India, I believe it was. We get the integers, where we start adding in the negatives into the mix. From there, we started adding fractions. So those are our rational numbers. Things like 1/2, 1/3, negative 18/30ths, whatever. Anything that can be written as a fraction. Then we added in numbers that can't be written as fractions. These are irrational. So these are numbers like square root 2 or pi, or later on this year, we'll deal with a number called e. So these are all irrational. If we put all of these together, all of them make up what we consider the real numbers. Now we're going to add to that. We're going to go beyond that point. And we're going to start talking about complex numbers instead. Complex numbers at basic levels are actually really easy to work with. We can work with it just like any other letter or any other constant. And that's what we're going to kind of do today is we're going to talk about how to do basic operations with complex numbers. Complex numbers basically include all the real numbers and anything that involves I. So it includes all of it at once. So let's start looking at that I and how we can kind of mess around with it. So I in of itself works like anything else that we're kind of used to. So if we had 2i and we added 5i, that's just 7i. It works just like x or a or any other indeterminate that we might have, or any other constant we might have. We can subtract with it. We can say 5i minus 7i, that's just going to be negative 2i. That still works the same. So most of what we do is pretty easy. Oftentimes, when we talk about an entire complex number, we'll have a part that goes along with it next to it. So if I have 3 plus 2i, these aren't like terms. So it follows the same rules as we had as x's. So when we deal with complex numbers, I'm going along with that guy's great job of conning everyone. We have a real part, which is our 3, and then sometimes we'll call it an imaginary part, which is the I part. Again, bad name. They're not imaginary, and there are actual real life applications for I's. We'll talk about one of them toward the end of this. So when we look at these, we have a real part and imaginary part here, and they can't combine. They're not like terms. It's easiest to think of it as just like terms. So I can take a complex number like this with a real part and an imaginary part, and I can add it to another complex number. So if I had 3 plus 2i added to 5 minus 5i, we can still do this. It works just like working with anything else. So we combine like terms. I's can't go along with regular numbers. So I have a 3 and a 5 makes an 8. A positive 2i and a minus 5i makes a minus 3i. And that's it. Subtracting them, we want to subtract two complex numbers. Say 2 minus I minus, and here the negative is going to work like distributing as well. Minus 4 minus 5i. I'm just making up numbers here. We can distribute the negative and then combine like normal. So this is 2 minus I minus 4 plus 5i. We combine our like terms, the reals go together, so that's negative 2. And then the imaginary parts go together. So minus I plus 5i is plus 4i. So adding and subtracting works great. Nice and easy. We do it the same way as normal. Multiplying, still pretty easy. So let's try multiplying two complex numbers. So when we multiply complex numbers, say 2 plus I and 3 plus 2i as an example, this is just foiling again. We're just going to FOIL it with one little weird part at the very end. So if I go to FOIL this, I have firsts, so that's 6. Outers, 2 times 2i is just 4i. Inners, 3 times I is plus 3i. And then last, and I get plus 2i squared. Combine any like terms, so that's 6 plus 7i plus 2i squared. And this is where we have one extra little part. So at the beginning of this, we defined I to be the square root of negative 1. So what's I squared then? Well, let's see. If I square these, I get I squared. And remember that a square and a square root cancel out. I squared is just negative 1. So I can come up here and any time in any of our work, we get an I squared, it just becomes a negative 1. So that's 6 plus 7i plus 2, the I squared is negative 1. So 6 plus 7i minus 2, and we get 4 plus 7i. So multiplying complex numbers is just distributing, it's our FOIL system again, with the only thing that when we have an I squared is negative 1. So let's do one more multiplication so you can see it. So 2 plus 3i times 4 minus I. So we go ahead and FOIL, just like we were going to FOIL anything else with x's or y's. 2 times 4 is 8, minus 2i, plus 12i, minus 3i squared. We can combine like terms. So that's 8. Negative 2i plus 12i is plus 10i. And now I squared is just negative 1. So negative 3 times negative 1 is plus 3. So we get 11 plus 10i. So that's multiplying complex numbers. Let's see. We'll do an example of dividing. Dividing is actually kind of the hard part for this. And it follows kind of similar to what we did with our roots before. So when we go to divide complex numbers, say 2 plus 3i divided by 1 minus 4i. These aren't like terms. They don't go into each other. We can't do much. But we still have the same problem that we had with roots. We can't have something weird like a irrational number or pi or square root of 2 or I in the denominator. We have to get rid of I. To get rid of it, we're going to do the exact same process we did with roots to get rid of it. We're going to multiply by the conjugate. So again, the conjugate is whatever is there, just with the opposite sign. So I'm going to multiply top and bottom by 1 plus 4i. Now top and bottom now become a FOIL problem. So I can actually FOIL both top and bottom. This works because remember, when we do difference of squares, which is effectively what we're doing here, it's going to cancel out all the terms with i's, and I squared is just -1. So at the end of this, there'll be no more i's left in the denominator. So up top, we get 2 plus 8i plus 3i plus 12i squared. On the bottom, we get 1 plus 4i minus 4i, and then minus 16i squared. Top and bottom, we simplify. Remember that I squared is just -1. So that's 2 plus -12 is -10 plus 11i. On the bottom, positive 4i, negative 4i cancel. I squared is -1, so that becomes a positive 16. So 1 plus 16 is 17. That's what we mean when we consider dividing by complex numbers. Is we're going to write it out as a division problem, as a fraction, and then we're going to multiply top and bottom by the conjugate. All right, those form our basic operations. We're not going to get anything else crazy with complex numbers yet. It's actually a whole branch of kind of its own mathematics. I took actually a full course on just complex numbers and how it interacts with geometry, how it interacts with calculus, real world applications of it, all kinds of stuff. So it's kind of its own mini whole field of math. This is about as far as we're going to go with complex numbers. There are a bunch of applications. I'm going to give you one big application right now. We'll just do one small example of it. So kind of the two easiest applications of complex numbers involve water flow and pipes and involve electricity. I don't know how far or what kind of engineering you guys have done, so I'll just give you a real quick breakdown as an example problem of this. So when we go to show a circuit that has electricity running through it, we use certain symbols for it. So as an example of those symbols that are used, you can use something that looks like this, almost like the little heart rate things you see in bad television dramas. That's the sign for a resistor. It's something that kind of doesn't want to let electricity go through it. Other things could be like an inductor. Inductor symbol is almost like a whole bunch of cursive L's that does stuff. Symbol for, let's see, we could have an EMF source or a source that's pushing electricity, could look like something like that. You can have capacitors where it stores electricity. So there's a whole bunch of these little symbols. And we don't need to go into a whole lot of detail on it, but one thing that does talk about complex numbers is kind of how much this whole thing, all the stuff in the circuits, how much of it does it resist the flow of electricity? And that's called impedance. So impedance is a measure of how much electricity is kind of getting forced to resist going through something. An individual thing is called resistance. Inductors and capacitors have reactance. It works very similar to resistance. But when we look at all these, there's a couple of weird things that we notice. When we did these, we actually get that, in particular, inductors and capacitors both give complex numbers for resistance. I'm not going to make you guys do a bunch of these. No, I didn't even include one. We'll kind of see what happens with it. So let's say, for example, I'll do a quick circuit diagram. We have a resistor up here with a resistance of 5. Resistance is measured in ohms, which is kind of a funny horseshoe symbol that I'm really bad at drawing. Maybe we have, say, something else that's affecting it. Maybe this one is like 4 ohms. Now let's put a couple more things in there. How about we have, maybe it's plugged into the wall or something. So we have a symbol. This symbol here would be like a alternating current source. So your walls in your house use alternating current. When you plug something in, it goes into an alternating current source. And let's have, say, an inductor. How do you draw that sideways? There we go. And the inductor is running 3 ohms. So this would be an example of a circuit diagram that would be used. This is kind of a weird circuit, honestly. We have an inductor, capacitor, and a resistor here. So if we want to talk about impedance then, when we measure impedance, we can make a little chart of it. So resistors don't do much. The impedance of a resistor is just whatever the R rating is. So if we have 5 ohms, it's going to give us an impedance of 5. A capacitor, all right, a capacitor is actually going to give us an impedance of negative, whatever the capacitance rating is, or whatever the resistance rating of that capacitor is, I. If we wanted to talk about an inductor, as an example, an inductor would actually give a rating of Li, where L is kind of the inductance that we're looking at here. So if I wanted to figure out the total impedance of this circuit, I can go around looking at the different objects in it and converting it. So as I go around this circuit, I have an inductor here with 3. So that would be 3I impedance. The resistor is just 5, so that's 5. Capacitor is 4, so we'd actually get minus 4I. Alternating battery is the source. It's not really doing anything to stop it. It's what's giving it. So the total impedance of this would be 5 minus I. I'm probably not going to give you many of these because I'd have to give you the reference charts for it, but I did want you to see that it actually has real world applications in spite of everyone calling them imaginary numbers. All right, so that's kind of it. So just as an overview, we looked at how to reduce roots today. We looked at how we can solve quadratic equations by taking square roots of both sides after we solve for the squared portion. And then we talked about the basics of complex numbers, what they're formed, how to work, how to add, how to subtract, how to multiply, and how to divide. It's kind of a lot. The complex number stuff is a little bit new. So just do the best you can with it, and we'll see how you do.